Hello everyone, my name is Horace, and in this video we're going to be going through LeetCode number 322 coin change. For this problem we're given an integer array called coins, and this integer array represents coins of different denominations and an integer amount which represents the total amount of money. We want to return the fewest number of coins such that we can make up this value amount. And if that amount of money cannot be made up using any combination of the coins, then we want to return -1. And we can assume that we have an infinite number of each of the coins. So we can use as many ones, as many twos, and as many fives as we need for this example. So starting off with this example, we want to see which is the minimal combination of coins such that we can reach the amount 7. Well, what is one approach to do this? We can start off with one approach, which is to be greedy. Now, being greedy means that we take the highest number coin that is available such that the amount is not negative. And I'll show you what I mean. We can start off with the largest number coin first. We can imagine there's some pointer here. Now, the largest coin that we can see right now is 5, and 5 is going to be less than the amount. So we know that we can fit at least one 5 into the amount. So we can go ahead and say that we use one 5 coin. Then the amount we want is 2, which is simply 7 minus 5. So then we can see that 5 is going to go over the amount, so this is not the value that we need. Then we move the pointer backwards and see the next largest coin, which is 2. And we check to see if we can fit 2 in the amount, and this is exactly the amount that we need. So 5 plus 2 is going to give us the amount 7. And this is going to be the minimal combination of coins such that we reach the amount value. And the reason we know that this is the minimal amount is that we can take a look at a different combination of coins. For example, we can have something like 5 plus 1 plus 1, and this is also 7, but here we're using 3 coins instead of 2. Another option is to use 7 $1 coins, so we can have 1 plus 1, so on, 7 times, and that's going to equal 7. And this is going to use 7 coins. So we can see that as we move downwards in the coin denominations, we get a higher coin amount that we need. So is the solution really that simple? Can we just be greedy and solve the problem that way? Well, that's not really the case because we can find a counterexample to using the greedy algorithm. So we can take a look at this arrangement of coins that we're given, and the amount is still 7. So let's try being greedy and take the largest coin value that we can. So first we can take a 5, and the amount becomes 2 that we need. Well, we can't take a 4 because 4 is greater than the amount. We can't take 3 because 3 is greater than the amount, but we can take coins of the 1 denomination. So we can take 2 of these coins and we'll get 7. And this was one of the solutions before. We didn't really change anything by introducing different coins. So now this is one of the solutions, but is this the optimal solution? Well, no, because we can see that there exists one solution here by taking a $3 coin and a $4 coin, and this will give us 7. And this is using 2 coins, while the example above is using 3 coins. So clearly this method is going to be much faster, but we did not use the greedy algorithm. So we have to find a different approach to solve this problem. We can take a look at a brute force approach to solve this problem, and that's by listing out each of the possible paths that we take from the amount. So let's say we start from the amount 7, and we can either use a coin of 1, a coin of 3, a coin of 4, or a coin of 5. So we can kind of draw paths like a tree, and each of these paths is going to have some denomination. So this is path you taking the $1 coin, this is going to be the path taking the $3 coin, 4 and 5. And then from each of these values, so let's say we took the $1 coin, it's going to be the amount minus that value. So it's going to be 7 minus 1, which is 6, 7 minus 3, which is 4, 7 minus 4, which is 3, 7 minus 5, which is 2. And then we can continue this for each of the resulting options. So let's take a look at the amount of 3. We have, again, 4 paths. We can either take the $1 coin, the $3 coin, the $4 coin, or the $5 coin. So 1, 3, 4, and 5. And if we take the 1, we'll get a value of 2. And then if we take the 3, we'll get a value of 0. This is very important. If we take 4, then we'll get -1. And if we take 5, we'll get -2. And it's very important to notice the negative values. These are indicating that we've gone too much over in the amount, so these are already not possible. However, we also see that we have a 0 value, and this is exactly what we need. And as we saw before, the combination of 4 plus 3 is going to give us 7, and it's only going to use 2 coins. So this is one solution to solve the problem, but the time complexity is going to be very high because we're computing a lot of the same values again and again. For example, if we compute the value 2 here, we won't need to compute it here if we just store this solution or the number of coins to get to 2 in some cache. And this is exactly the approach that we're going to use. We're going to use something known as dynamic programming. And the way we will cache all of the resultant values is we're going to keep some array, and this array is going to be called, let's say, dp, and it's going to have all of the values. So let's say the dp of 0 is obviously going to be 0. We can start off with that. And let's say to get to a sum of 1, dp of 1 is going to be 1, and so on. Now this approach is something that's known as bottom up, since we're starting off with the 0th value and we're going outwards until the amount value that we want. So I'll write out the dp array values and then we'll calculate dp of 7. So now that I've written out all the dp values until 7, let's go ahead and calculate dp of 7. Since we've already calculated everything before it and the amount of coins that it's going to take to get this sum, then we can just use that cached value, so dp of whatever, and then we just add it to the coin value so we can get the current dp array value. So I'll show you what I mean, and you can see that dp of 0 is going to be 0, since to get to a sum of 0 we need 0 coins. To get to a sum of 1 we can use one of the $1 coins. To get to a sum of 2 we can use 2 $1 coins. To get to 3 we have a $3 coin. To get to 4 we can use a $4 coin. To get to 5 we can use a $5 coin. And then to get to 6 we need a $5 coin and a $1 coin, hence why it's 2. So each of the values here represent the amount of coins that we need to get to this sum. So to actually find dp of 7, we need to check the value against all the coin denominations plus the dp value minus the amount. So what that means is that, let's say we take coin 1, well then we're going to have to use one $1 coin plus the remaining sum, which is going to be dp of 7 minus 1, which is just 6. But we've already calculated dp of 6 right here, and that's going to be 1 plus 2, so that's going to take 3 coins if we use a $1 coin this way. But let's say we use a $3 coin instead. Well, then we want to instead calculate dp of 4, and dp of 4 is 1. So then we have 1 plus 1, which is 2. And this is currently our minimum value that we have. So then we continue to check the other coins. So let's say we use a $4 coin. This is going to be dp of 3, and dp of 3 is 1. And we again have 1 plus 1, which is 2. So this is going to just be the minimum, so we don't have to update anything. And then if we check and use a $5 coin, well then we can check this, and then we see that we have dp of 2, which is going to take 2 coins. So 1 plus 2 is going to be 3. 3 is not less than the minimum, so this is exactly the amount of coins that we're going to return in the final amount. So we can just return dp of 7 in the end, and this will be our answer. And if we talk about the time complexity for this algorithm, well, it's going to be big O of the amount times the number of coins. So let's say the len of C, which is representative of coins. So this is going to be the time complexity, since we have to calculate the dp values of all of them using each of the coin denominations. So the space complexity is going to be big O of amount, since we have a dp array going to amount plus 1, so we start at 0 and we go to amount. So this is going to be a space complexity of big O of amount. So with that being said, we can go ahead and write the code for this algorithm. Okay, we're on LeetCode and we can start writing the code for this algorithm. We can start off by initializing the dp array. So this is going to, let's say, have a maximum value of amount plus 1, since we want this value to be higher than any of the coin values that we can get. And this is going to be helpful when we're returning the final answer. We can verify if it's not less than or not equal to amount plus 1, because it's going to be updated otherwise. So we can multiply this by amount plus 1, and this is the number of elements, since we have to go from 0 to amount plus 1. Then we can put in the 0th index for the dp array, which is just going to be 0. Then we basically want to loop over from 1 to amount plus 1, since these are the values that we're going to basically add to the dp array. So for, let's say, amount in, or a in range, we'll start from 1 and go to amount plus 1. This is going to be exclusive, so it's gonna go to amount. Then we can say, then we want to basically loop over the coins. So for C in coins, and we want to check if we can take that coin as a potential value. This means that subtracting the coin value from the amount will not be non-negative. So if A minus C is going to be non-negative, then we can use it as a potential value. So dp of the A value is going to be the minimum of the dp of amount, which is what is currently stored there, or it's going to be 1 plus the dp a minus c. And this 1 value comes from the coin that we're using, this a minus c coin. And then dp of a minus c is just the amount minus the coin. So this is the remaining sum that we want to find, and then check how many more coins we need to get to that value. Then finally, we want to return dp amount, or dp amount if the dp amount is not equal to what we initialized it before, so amount plus 1. Otherwise, we can just return -1. That means that it was not updated, so there's no correct value or no way to get to this value. And this should be the answer, so we can submit it. And yeah, it's accepted, and you can see that it runs perfectly fine, and this is the optimal dynamic programming solution running in big O of amount times the length of coins time, and has a space complexity of big O of amount. So with that being said, hopefully this video helped you and you learned something, and I'll see you soon.